There are still seats here if you guys want to sit. It's fine. All right. So my name is Andrei, and I'm really passionate about open source software and data visualizations. Now let me introduce myself by showing a few of my recent projects. In this project, I'm doing a pathfinding on the graph. This is a JavaScript library which allows you to quickly find shortest path between 2 points on the map. And this map is very large. It has 730,000 nodes, and the time to find the path usually is under 100 milliseconds. So I'm super passionate about graphs and algorithms on the graphs. I'm also very passionate about maps. In this project, you can select an area on the map and download every single road in this map with a very, very high level of the details. Not only highways, but everything. Once you have this area, you can print it on a map. So now you have a map. And you can have personalized experience on your travels. And this is all open source. You can go download the source code and modify as you wish. In this project, you can see distribution of colors in any image in the form of a histogram. So I really love animations and visualizations in the browser. In this project, you can see visualization of every single NPM module in the shape of a galaxy. So you can explore it. This is AngularJS cluster here. So I'm super passionate about JavaScript and NPM as well. Finally, topic of the today is a vector field visualization. I'm going to show you how to visualize vector fields, and I'll explain what vector fields are. And this is the project that we're going to be talking about. And when I was preparing for this talk, I was a bit terrified because I know how to visualize vector fields, but I don't know why would someone want to visualize them. Other than they look cool. They really look cool. So if you know a reason why would somebody want to see vector fields, let me know. Otherwise, just assume it's cool. All right. So how did I get into this problem of vector field visualizations? I was very passionate about procedural generation of the cities, and I found this paper a couple of years ago which describes how to generate cities using tensor fields. Well, I have no idea what tensor fields are, but the results that they presented here, this is all generated procedurally, were really amazing. I really enjoyed how they look like. So I thought I really should understand this paper. So I decided I have to implement something to do this. Unfortunately, I'm not a very fast learner, so I decided to simplify the problem from tensor fields into the vector fields. Vector fields are more accessible to me, and that's how I got into the vector fields visualization. But what is a vector? I know what a vector is. It's just basically an arrow which has a direction and it has a size. That's what a vector is. Okay? And what is a field? Now, everybody knows what a field is. This is a plane where you see wheat grows. At every single point, you have some crop it's drawing. So now what is a vector field? In fact, it's the same idea, but instead of drawing wheat, you grow vectors. In every single point of this two-dimensional plane, you grow vectors. This is a very pretty field where vectors grow in the same way. Doesn't have to be that way. Vectors could grow in any directions. They could be very dense as well, like in every single point you can have a vector, or they could be very random, pointing in different directions. These are all vector fields. So how do we visualize a vector field? One way to visualize it is just by using arrows like here. Right? For nice fields, they look kind of nice, but for massive fields where you have different sizes of an arrows, it doesn't really look good. To understand how to visualize them, it's also interesting to understand what these vectors represent. Very often they represent some sort of change, or like speed, change of the speed. For example, if you look at the winds that are blowing on Earth, right, in every single point you have a direction where wind blows, and you have a strand, how fast this wind goes. So you can represent this, think about these arrows like speed of the wind blowing on the Earth. But how can they see wind? Wind is invisible. It just blows particles of the oxygen, so it's hard to see. What if we just throw a bunch of particles, dust on the wind? We will see much, much better. This is exactly what this tool is doing. You see lots of particles are flowing. This is the same vector field. We can increase the number of particles that are flowing in the same direction. And there are a few parameters in this tool. For example, every particle can leave its own trace. How long is the tail of a particle after it flows? But also, if we let particle fly indefinitely, if they keep flowing away, eventually the field gonna just dissipate because all particles are blown away. So to prevent that, I have this particle reset probability, which allows me to kill a particle at a certain time with a very small probability and then resurrect it somewhere in a different place. Right? That's the particle reset probability. You can reduce the particle reset probability, but it doesn't give much space because they're just killed too often. So just drop in a bunch of particles and see the vector field. But how do we define the vector field? Well, you can just describe in every single point. You can encode the actual vector. What's the x coordinate? What's the y coordinate of the vector? So you can read from this image and see where the vector is plotted, or how the vectors are defined. Another example is just to use a function, because usually vectors represent some sort of rate of change. I call this function get velocity. X and y coordinates here represent the input, like on the plane, what's the x and y point. And the output of this function just gives you what's the vector in that point. So if vector velocity x is 0, it means nothing flows horizontally, but everything flows vertically, because y is equal to the input y. So the higher you go from the origin, the higher is going to be y, and that means that the stronger wind going to blow. So it looks like this. You see, it's very slow here, but the farther you go from the origin, the faster you grow. You can change it to x. So now, the farther you go horizontal on the plane, the faster you're going to go on the y direction. Or you can change on the y coordinate. So here you see, now x depends on the y, so the higher you go on the y, the faster it goes on the x. But now, if you combine them together, you're going to get a circle. Why is that? You see, this direction goes like this, in one side and another, and this direction goes like this. So they kind of pushing each other. Turns out this is a differential equation of a circle, this simple formula, and it's very easy to see with this tool how to define a circle. But now, we know how to define vector field now. We know what vector field is, but how do we find where to put the particle? What's the next position of the particle? Because all we have is just rate of change. We have these tangent lines. We don't have the actual blue line. This is the actual trajectory, but all we have is just this red one. How can we tell where should we move the particle? In mathematics, they use different methods to solve this problem. And the intuition here is, since this is a tangent line, let's do a very, very tiny step on this red line. And you see it's very close here. Like it's very, very similar to the blue line. If you step too far, you're going to probably overshoot. So it might be not very accurate. This method called this Euler method of solving this equation. And there are more complex and more accurate methods of solving this equation. Here, instead of solving just for one tangent line, we take 4 different tangent lines and take their average to predict this green point over here, which gives much, much more accurate results. But every single k in this formula, it depends on your step, how far you step on this red line. This thing is called integration time step. And if you're familiar with machine learning, very often when you optimize a problem, you solve a machine learning problem, you also have some sort of gradient descent where you have to pick this method, pick the step of the solution. So it's important to pick it correctly, because if you pick it too large, you can just overshoot and solve the wrong problem. To give you an example, here we have a bunch of particles flying, right? They all describe the circle that we saw before. An integration step is set to 0.1. But if we make it very high, you see that they're overshooting, they're not solving the correct problem, and they just start converge to something that is not a good solution of the circle. So, but this blue line, it describes the trajectory of a single particle. On this visualization, there are 10,000 particles. We can go to 100,000 particles, or even 1 million particles. It's still very fast. So how can we solve this quickly? We cannot solve this directly using CPU because there are so many equations, and we have just 16 milliseconds to solve on every single frame. So I turn to WebGL to solve this problem. And WebGL is a very simple state machine which you have to set up first. But all it allows you to do is read the color value from an image and write the color value to the screen or to another image. That the other image usually called the frame buffer, but all we have just operation with the colors, nothing else. Right? So what if we represent the position of a particle as a color? So we basically have to encode float variables into the four-dimensional RGBA color format. Using these two functions, you can easily do the translation between color and float values. So now we can pack floats into images and read them back from the images. And the entire solution for the differential equation is written in this GLSL program, which is a WebGL programming language. And it's exactly what we described before. We read from an image, the input was the current positions of the particle, and then we read what's the change, how fast should we go, we set a new position, and write the output. The beauty of this solution is that it operates in every single pixel by the GPU, so it's very, very parallel. You don't have to do this sequentially. And here we have the example of frame-by-frame rendering. Basically, every input is written to the texture A, to the input image, and the output is written to the texture B. It's not something that you see on the screen, it's just image on the background. So we compute the new position of the particle and write it to the texture B. On the second frame, we just swap pointers on the client side. We do not upload new images to the GPU memory. We just swap pointers, say, now you know what, texture B is your input, and write output to the texture A. And texture is just an image, fancy word for image. And you keep doing this ping pong game in WebGL. I feel like I'm losing people. Sorry. One problem with this approach was that we have vectors which are two-dimensional. We have x and y, and color is 4 bytes. So we have to split the color 2 bytes for x and 2 bytes for y. And precision here was not very accurate. It was a very mysterious problem for me. This is a visualization of a circle on a desktop. This is visualization of a circle on an iPhone. So in iPhone, for some reason, that packing algorithm produced this banding where you see strange areas which should not be there. Even worse, this is a vector field with zeros everywhere. So there should be no movement whatsoever unless those particles that survive and die with small probability. But here on iPhone, for some reason, you see that movement, there are particles colliding. So it's not correct. So I had a crazy idea. What if instead of using a single texture for 2 dimensions, what if I just use one texture for the x-coordinate input and one texture for the x-coordinate output, one texture for the y-coordinate input and one texture for the y-coordinate output. So instead of solving just 1 million differential equation every 16 milliseconds, I would have to double the work and solve 2 million differential equations. I really wanted to be performant, but it's like, how could this be performant if we have to do repetitive work? And it turns out it was not actually a problem at all. I tested in a very, very old device like Android which I bought for $30 on Amazon. It was still very fast. So this was an example of premature optimization in mind, which I didn't want to do in the first place, but eventually it turns out quite well. Like, it's still very fast. Don't optimize too early. With this tool, I also found a few mathematical insights that I wanted to share with you. One is normalization. In normalization, what you have is you basically have some sort of data, and you bring the data to the range from 0 to 1. Right? But what does it mean in terms of a vector field? To bring the data from 0 to 1, you basically divide the vector by its length. So here I'm going to do that. see, since it's all from 0 to 1 and the time step is the same everywhere, the speed of the vector field is also the same everywhere. So that's example of normalization. Just brings the vector to the same speed everywhere, regardless of your original distribution. So here you see, if near the 0, it's not moving fast. It goes further, it moves faster. But as soon as you normalize, it just everything uniform. So the learning is the same everywhere. The other interesting insight is that 0 is an amazing number. I know I'm excited about random stuff, but 0 plus x equals x. This is fantastic. Why is that so? Imagine you have this circle that is spinning and defined as a vector field. Now imagine you count the distance to the center of that circle, right? The farther you go, the longer is going to be the distance, the higher is going to be the distance. And that means that 1 over the distance is going to be smaller. It's going to approach to 0, like this line approaches to 0 here. The farther you go from the center, the smaller this becomes. What this means for the vector fields, let's see. This is the same circle here. You see that the movement here is very fast, and nothing happens here, in this area. Right? Which basically means, and how this is achieved, you can see here, I'm dividing by 2 lambda, the distance to the center. Not just distance, but distance to the power of 3, so it's even stronger. But now I can add fields in the different places. Just add one more. Since there was no movement, it was 0. 0 plus x equals x. And here this field is very strong. So this allows you to combine vector fields in a new way, like this. Or you can take this idea to actual extreme and say, what if we're going to start spinning circles around every single place here, or every single dot here? It becomes this unrealistic, futuristic images or something. And you can still see the individual movements there. So in machine learning, there is this concept called radial basis functions, which allow you to construct new features in your data set. And radial basis functions are basically functions that depend on distance to certain objects. And this gives you insight into why distance is very important, because if you do something 1 over distance in 3rd degree, you can combine things together. Well, I thought that was crazy, but somebody on the internet actually proved me wrong, and they created even crazier thing with this thing. They called it Eye of Sauron, and eventually
It's a perfect use case for a custom cursor.
There are a few user experience insights that I learned from this tool. First of all, I was thinking about Apple users first, because when I was imagining this tool to be released to the public, I thought that people were going to read it on Reddit or Twitter, and they thought it should load really fast. So instead of loading this configuration dialog, which is driven by UGS has 68 kilobytes of size, I decided I'm going to split it into the chunks. So I load first WebGL rendering. So if you open this page on the mobile phone with a very slow connection, it's going to immediately start rendering the field, and eventually you're going to see the UGS settings appearing. So that was first split into the chunks, so that it's faster to load in the mobile. Then second, I thought people on mobile, they wouldn't be entering the vector fields by hand, so I came up with this button called randomize. Every time you click this randomize button, it's going to create some random field. So that allows you to just play with this until you find something pleasing. And another third insight, I wanted to make this tool very easy to share. So every time I change properties here, let's say color and velocity, I change the placement of the string. I actually update the query string here. So there is no persistence whatsoever, but you can just copy query string, open the view tab, and you're going to see exactly the same vector field. So that's easy to share. And I think these few ideas, they allowed me to have very successful project over a course of its lifespan. I had more than 100,000 visitors. I think it's So in summary, vector fields are just fields where you grow not plants, but vectors. And it's easy to solve everything on the WebGL. The source code for this is also available. If you're curious, you can learn. But also I wanted to share one last thing. Instead of dropping particles onto the canvas and making them fly, another way to visualize the vector field is just basically let the particle fly as long as it can until it meets another particle, another line, right? So this is a visualization of winds 1 year ago on March 14, 2018. I downloaded this data from a government website and created a vector field because winds are vector fields, right? And the brighter it is here, the stronger is the wind blowing there. And today I wanted to share with you an animation of all winds blowing through the year 2018. I never shared this particular animation with anyone, so hopefully it will work. Said that nobody ever figures out what life is all about, and it doesn't really matter. Just explore the world, and nearly everything is really, really interesting if you go deep enough. So I really thank you guys for letting me introduce you to the journey into the vector fields. Thank you so much. Cities. But to be honest, I have a huge dream of visualizing the internet in a different way. I think we have imagined an internet as a search part, but it's not that. I want to find a way to present internet as a visualization of the cities maybe or but thank you for the question. Yes?
That last animation,
Yeah, I rendered actually everything offline in Node.js to the images, and these images are like this. You can see they're very high-level images with lots of details, and it's actually not Node.js, it's rendered offline using Node.js. Yes, please. Oh, you're asking if it's possible to compute in multiple dimensions, not necessarily in two?
Yeah.
Yeah, it's possible, but not within this user interface because I don't know how to reset particles. It's totally possible to scale it to multiple dimensions, but how to navigate in that system is still not clear to me.
Okay, yeah, you can add one more dimension as well.
Thank you.
How long did it take to after that?
This visualization or to build the tool?
Or probably to
build the tool, it took me around 1 month of work every day, but not like 5 hours a day. It's more like 30 minutes a day. Yeah, and this visualization took around 14 hours to render. If If you guys have more questions, please ping me on Twitter. I love this stuff. Thank you so much for